Okay, this is the second of the videos. I'm trying a slightly different format so that you can see what I'm drawing, because I don't have a whiteboard while working at home. Let me know how this works. Additionally, I've got a baby in one hand, so might be slightly distracted. Apologies in advance. So we talked last time about using calculus to derive the equations of motion, and we'll discuss that again in tutorial. The next bit of knowledge we need to advanced higher physics is kind of a gap in the classical physics that we've studied so far. Up until now, National 5 Higher, we've only looked at what we call linear dynamics. Okay, so when we talked about the speed of objects, we say, you know, the velocity moving from A to B in some kind of path, whether that's a projectile, but it's always starting in one spot and going to another. However, what that doesn't account for is all the objects in the universe which are spinning, things that are rotating. So say this journey's been taken, you know, a car can drive from A to B and have some displacement, but equally, if it's on mud, it might just spin in place, you know, wheel spin, in which case the tyres spin around, the car doesn't go anywhere, but definitely something's happening. You know, there's mud getting kicked up, there's energy stored in here. Okay, so this rotational motion, it can't be ignored for the wheel of the car. Similarly, if you think about bigger scale, although the objects in the room that you're in probably aren't spinning very much, what we're standing on is planet Earth. And planet Earth spins once every 24 hours, okay? So when you think about planets, well, they're all rotating. I'm thinking about the moon is rotating around the Earth. The Earth spins on its axis, and the whole system is rotating around the sun. If you zoom out a bit, and our entire solar system is rotating around the star in the middle. Okay? And you zoom out further, and not only is the solar system rotating, but that solar system is orbiting around the centre of our galaxy. And our galaxy, the Milky Way, is also rotating. If it wasn't, it would all collapse in on itself, so it's a pretty good thing. And these objects have been rotating since, you know, the solar system's been rotating for 4 billion years. Oops, I'll stop the picture. The solar system's been rotating for 4 billion years. The galaxies have been rotating for billions more. So in the big scale, the whole universe is rotating. And in the small scale, we think about how we've described atoms so far. We're going to come back to atoms later on and give a better, more quantum mechanical description. But for now, we're kind of sticking with what we call the Rutherford model. We have the idea of protons and neutrons in a nucleus, but the electrons perpetually orbiting around the outside. Okay? So this Rutherford model also says that all the electrons in your body are constantly rotating all the time. So up until now, higher National 5 physics haven't given us any way to account for this, and so there's a pretty big gap that we're going to fill in at advanced higher level. The good news is, it's not really any harder, it's just kind of new symbols. So once we get used to the new symbols, we're going to see that the actual process of using these quantities, it's not really any different. Okay? So, first of all, before we can do anything else, we need some quantities to apply. Okay? So things we could measure in linear motion, linear dynamics, was the displacement of an object, its velocity. We realised later we needed to add a velocity at the start as well to work out the change, and the acceleration of that body. Okay? The rate of change of velocity. Well, all of these things have rotational analogue. And basically we just add the word rotational to the front. So if you can think about the distance that an object travels from A to B, its linear displacement, you can think about its rotational displacement. Okay? So we have rotational displacement. And how are we going to measure that? Well, if you think about something moving through rotation, the best way to describe how far it's gone is to think about the angle that it's subtended. So we're just going to measure an angle. So we can use theta. Okay? Now, for reasons we'll get to, that are really, really useful, it's far better to measure that angle in radians than it is to measure it in degrees. Degrees we've just kind of guessed that. Radians are going to make our lives a lot easier. You think, well, why use radians? It's got all those pi's. The pi's cancel out. Okay, so we'll get to that in time. Instead of velocity, so sorry, I called this rotational displacement. It is of course angular displacement. I'm tired. So we've got angular displacement. We're going to have angular velocity. Okay, and then we can't run out of symbols. So we're getting into Greek. Okay, so theta is a Greek letter. We're going to use the lowercase omega. The lowercase omega for angular velocity, which looks a bit like a curly W. And if angular displacement is in radians, then angular velocity must be measured in radians per second. Okay? So initial velocity just becomes a bit of a mouthful, but initial angular velocity. Rather than give it its own symbol, a completely new letter, we're a bit more space saving, because it's just an angular velocity at a specific point in time. It's just the angular velocity at whatever time we choose to be zero, whatever time we choose to be the start of the system we're looking at. So we can just call it omega with a subscript 0 for basically the angular velocity at time 0, or initial angular velocity. And again, we're going to measure that in radians per second, because it's just an angular velocity. Okay. Acceleration becomes angular acceleration, which I think hopefully makes sense. And that's thinking about, well, is this object speeding up its rotation? If you think about the Earth, it's pretty steady. It's 24 hours for every rotation, so its angular acceleration is 0. It just takes 24 hours to rotate every day. But if you imagine someone spinning, spinning up, think about a car tyre spinning up, well, it's going to accelerate. It's going to start at 0 and it's going to get faster and faster and faster, so it's going to have an angular acceleration. The symbol we're going to use for angular acceleration is alpha, which we've seen before as a symbol for alpha radiation, but here in these equations we're using it to represent our angular acceleration. And again, if angular velocity is in radians per second, then the rate of change of that is in radians per second squared. Okay, so we've got some new units to use. They'll become familiar with you through use. Basically, you'll get them. Okay. Well, so what we're going to do with them? The first thing to say is that there must be a link, right? If you think about an object moving in a circle, so I've got a circle here of radius r, and this blue path shows an object rotating around. If you think about it, there must be a link between the linear displacement, how far it travels around the circumference of this circle, and the angular displacement, okay, the angle, the increasing angle that it subtends over time, okay? So this angular displacement theta and this s are linked, okay? The further you go around the circle, the bigger the s and the bigger the angle. And they must be linked. It can't be that hard to tie them together. So let's have a think about that. And the simplest case is to take a path that we know really, really well. The path around the circle that we know the best is the whole circle, okay? So let's consider one full rotation. Okay, so what's the displacement around one full rotation? Well, it's just the circumference of a circle. So S is 2 pi r, okay? So pi d, or 2 pi r, is the circumference of a circle, so that's your displacement for one full rotation. And what's our angular displacement? Well, that's just one full circle. And in radians, the radians for one full rotation, I hope you know from mathematics, is 2 pi, okay? So in order for me to combine them, well, I can just divide the two by each other. So S divided by theta is 2 pi r, divided by 2 pi, which is lovely because we've got some cancellation to do. And the 2 pi's disappear. This is why radians are great, okay? Because when you actually come to use them, you can very often cancel them out and you're going to get a simpler relationship. If you were using degrees, you'd still have a factor of pi in there, which we no longer have. So just rearranging this to be slightly tidier. The displacement travelled around the outside of a circle is always equal to the angle you subtend in radians multiplied by the radius of the circle you travel through. Okay? So we can convert really easily from 2b either by multiplying or dividing by r. Okay? And from there on it gets pretty simple, because sorry, I'm just going to slide across. When you think about what angular velocity is, well, angular velocity, omega, is the rate of change, is d by dt, of the angular velocity theta, which we've said is s over r. But the radius doesn't change with time, so that's a constant in our integration. Doesn't matter a damn. We can just take it to the front. So we're just left with ds by dt, which we saw in the first video. ds by dt is better known. Rate of change of displacement. It's just velocity. So we've got omega is v over r. So again, that factor of r didn't change. So we have v is omega r, okay? Which you can see is the same format, right? I took to go from the rotational component to the linear correspondent, to multiply by r again, okay? And by the same logic, differentiate this again, I'll get acceleration. But this is still a constant, nothing else will change. So the acceleration is going to be the angular acceleration alpha times by the radius. Okay? So very often converting between linear and rotational values is just going to involve multiplying or dividing by a factor of r. Okay. The next thing we can do is we can derive some equations of motion. We call it some equations of motion. Since the maths is the same, these equations are going to have exactly the same shape in both rotational and linear form. Okay? Oh, to have two hands free. So our equation for linear motion at a constant velocity is s equals vt. So it stands to reason that for rotational, I can just substitute them out and say, well, instead of displacement, I'm looking for angular displacement theta. Velocity is going to be replaced with angular velocity omega. Excuse me, I need to just slide this down, but I can't write on it properly. Never try and make educational videos while holding a baby. So it's going to be omega t. This equation, I can just replace again each one with its corresponding, its analogue. So velocity becomes angular velocity, initial angular velocity becomes initial angular velocity, acceleration becomes angular acceleration, and t stays t. Okay, we can just do the same. So we're going to get a set of equations that are basically exact analogues of the linear equations, just using our new rotational values instead. Okay. I'm going to leave the video there because I'm going to try and chunk this up. This is enough to be getting on with. We can now solve all kinds of problems about things rotating. Our next steps are to consider, well, how do the forces making something rotate correspond? Because what we haven't got correspondence for, if we go back a few pieces of paper, well, acceleration, we're going to have to think about a bit deeper, Because if you think about something rotating, well, although if you think about the Earth, they said the Earth has no angular acceleration. It's not speeding up or slowing down. But there is some acceleration happening, because if you're standing on the Earth, well, at one time of day, you're up top of the Earth, and you're travelling this way with a velocity v. But 12 hours later, you're on the other side of the planet. And although you've got the same value of velocity, your velocity is now pointing the opposite direction. So there's been some change in your velocity vector. So we've got to come back to acceleration, and maybe we need to think about more than one kind of acceleration here. So that's an open question, is acceleration, how are you going to deal with that? Other values that we haven't found analogues for is, well, what causes linear acceleration as force? Is it just as simple? Is there a simple analogue for force and rotational, or is it more to it? We're going to have to look at rotational, about kinetic energy, because now we don't just have linear kinetic energy, we're also going to have rotational, and that's going to have some interesting effects. So that's our next step, is to think about kind of the forces. Sorry, I realised you couldn't see the drawing I did. So we're talking about being on Earth on one side of the planet, and you have velocity in one direction. 12 hours later, your velocity has the same value, but it's in the opposite direction. So there's been some acceleration. Okay, so we're going to have a look at that. We're going to have a look at the forces. How do you cause things to rotate? Because there's slightly more going on than there was in linear motion, and for that reason, we're also going to need something to correspond to mass. Because again, making something rotate isn't just as simple as saying, well, how much mass am I trying to spin? There's a bit more going on. So we're going to come back and look at all of these things next time.